Okay, let's start with the exercises now. All right. Yeah. So I'll show why any well-ordered set has the least upper bound property. So you take any set B such that you want the least upper bound for it, and then you take the set C, which is equal to the set of all upper bounds of B, right? And since C, which is C such that it belongs to A and is the least upper bound of B, is an upper bound of B. Then you take the smallest member of the set, and this will be the least upper bound. Why will it be the least upper bound? So I'll just call it C naught. C naught is the least upper bound of B because, well, it's an upper bound because it's a part of the set and it's the least member. And if there's anything smaller, then it contradicts the fact that we chose the smallest. So if it's well ordered, then we can find it. Okay. Every element has, except the largest, has an immediate successor. Okay. Question 2A. So, yeah, you take, yeah. For any element, let's say A belongs to A, right? A is a well-ordered set. We take the set B of all such set. So it's a simply ordered set too, right? So all B is greater than equal to A, no, greater than A, and B belongs to A, right? Yeah. Now we take the least member of the set. Let's call it B naught, and I'll show why this is the immediate successor. So that is because, let's see. Recall that the immediate successor is defined as okay, if so the interval a comma b is is empty implies b is the immediate successor of a, right? Yeah, that's the definition. So how do we show that this is empty? And this is recall the set of x such that x is greater than a and less than b, and x is in the well ordered in the simply ordered set, but it's also well ordered here. Yeah. So B naught, well, observe that if there exists C such that it's greater than B naught and greater than A, well, C is the least member now, right? C is a strictly lesser than B naught and it's greater than A, so it belongs to the set and we got a smaller member. That's a contradiction, and that's why this set must be empty, and that's why B naught must be the immediate successor, and that's how you get. Okay. Find a set in which every element has an immediate successor that is not well ordered. Oh yeah, if it's the largest, then so the largest element will not have for that. So essentially, you can only find the smallest member of a set if it's non-empty, and for the largest member of the well order, it will be empty. That's it, and there is no largest member, and that's why the except the largest statement was the clause was added to the statement. Yeah, in which every element has an empty successor. That's not well ordered. Oh, that should be easy. Uh-huh. Every element has an immediate successor. Okay, so mm, so the set of integers, positive integers, definitely won't work, right? And actually, yeah, the set of integers might as well. So yeah, every integer has an immediate successor, namely x plus one, and so you take the set of negative integers, it's not going to have uh, a least element. So yeah, it's not a well ordered. So yeah, the set of integers. Okay. Uh-huh. So I just proved that in generality, two well-ordered, uh, if two sets are well-ordered, their product in the dictionary order can be well-ordered. And I showed you how that works. So they are both well ordered, but in this case, they don't have the same order type for a very simple reason. Let's see, 1 comma 2 cross z plus. Well, observe that 2 cross 1 has no immediate predecessor. If it has any predecessor, it's going to be of the form 1 cross m, and there's an element between these two for all m. So because of that, there's no immediate predecessor here. But if you take z plus cross 1 comma 2, every element would have an immediate predecessor. How do you check that? Well, it's going to be of the form m cross 1 or 2. And yeah, you can just, if it's m cross 2, you can take m cross 1. And if it's m cross 1, you can take m minus 1 cross 2. So yeah, we have it. So because of that, we don't have the same order type. Okay. Yeah, this is a good problem. So A fails to be well ordered if and only if it contains a subset having the same order type as Z minus. Okay. So A is well ordered if it contains A fails to be well ordered if it contains a subset that does not have a least element. So if it contains Z minus, well, Z minus doesn't have a least element, right? So if this is the case, we found the counterexample. So one direction is done, which is this one, right? Now to prove this one. So yeah, A fails to be well ordered. Now, okay. So if A fails to be well ordered, there exists a subset B of A such that it doesn't have a least number, right? And it's non-empty. That's more important. Now, yeah. So okay, can we just choose an arbitrary one? Mm, okay, so B is definitely not finite, that's for sure, because otherwise any finite set can be well ordered. That's proven, I think. In any case, we can just actually it's well ordered because the integers are well ordered. Yeah. Now, fine, it's not finite, so we won't ever run out. That's one thing. Now, how do we define it? So ultimately, we need to use a recursive definition. That's the only way it works. Can we just take any? Yeah, fine. Let's take an arbitrary member B naught of B, right? Now, the set B minus B naught, yeah, the set B minus B naught is a subset of A, and since B has to be infinite, otherwise it would be well ordered. This is non-empty. So this also has a least member, and we define that to be B1. And observe that since hang on, A, oh yeah, A fails to be well ordered. Mm, oh yeah, choose B1 less than B0. This can be done because otherwise B naught would be the smallest element in B. And that's contrary to our assumption. This has no least element. And which means this was, yeah, BS. Yeah. So B naught is an arbitrary member, but there exists a B1 less than B naught because B naught is not the smallest member. So we choose that. Is it arbitrary? Possibly. I'm not sure now that we can if we can do it without choice. We might need choice for this. In either case, I don't care. We're using choice. Yeah, so we can choose a B1 that's less than B naught because this is non-empty, right? And yeah, you can define it basically for all integers, which would be, Bn would be less than Bn minus 1. And there exists such a thing because, yeah, and observe that we'll get a descending sequence, right? So is that fine? Yeah, so you can write in generality that Dm is less than Dn if M is greater than N. Okay, what else? Yeah, and so you can just map this suggests the order type bijection you'd want to create, right? So you just replace M with minus N, and then you can get the right bijection that you want. And this set that I'm defining, which is the sequence from B naught to, well, forever, which is descending, it's the same order type as Z minus. So you can check that. You have to create one goes to B naught, two goes to sorry, minus one goes to B naught, minus two goes to B1, and so on. Yeah, in the usual order. So yeah, it works out. Okay. Show that if A is simply, yeah, I think we just have to use the part A for this one. Let's see. So show that if A is simply ordered and every countable subset of A is well ordered, then A is well ordered. I think this works through a counterpositive. So let A fail to be well ordered. What does the statement say then? Well, A is given to be countable. So let's just write it here. And so every countable subset of A is well ordered. So there exists a countable subset that fails to be well ordered. Okay, now what? So this can happen if and only if it contains a subset of order type Z minus. See, right? And yeah, are we done? Okay, so but observe that essentially this is the same thing, right? This is proven to be equivalent. So now what? Yeah, it might just be equivalent. I'm not sure. Yep. So I'm not sure why it doesn't hold backwards too. Oh, A is not given to be countable. Okay, that doesn't matter too much, though, I think. So A fails to be well ordered, then there exists the B that has the order type of Z minus, and that means there exists a countable subset that's failing to be well ordered. That's fine. For the other direction, okay, maybe it there. I'm not completely sure. There might no, there shouldn't be a counterexample. So I think it's just a restatement of the same thing. So it might just be if and only if. But yeah, that this direction certainly works. So yeah. Okay. Show that the well ordering theorem implies a choice axiom. That's pretty simple. So, well, yeah. Uh, I'll show that the power set thing is equivalent to any collection of sets. Actually, yeah, this is a superset of collection A if so if A is the equal to union of A, which is let's see, yeah, fine. So I wanted to show the equivalence with the power set thing. Let's see. We take a collection A, right? And we take its union. So union A belongs to A. A is equal to A prime. Now, power set of A prime is going to be a superset of A. I think you can agree with that, right? So now what? Now, if we have a choice function from power set of A to the collection A, then yeah, since every member is going to lie in that, we can simply restrict the function and get the desired choice function. So I think one direction I showed and the other direction is this. So yeah, they're equivalent. Okay. So now what? Now, yeah, take any, so A is a well-ordered set. Take any subset of A, right? That's a subset. Now, its least, so given that A is well-ordered, this set will have a least member, and that least member A naught will belong to B. So we simply choose this to be C of B. Since C of B belongs to B by definition, right? We're done. It's a choice function. So yeah. Okay. Yeah. S omega is that. Show that S omega has no largest element. So let's see. Hmm. Okay. So suppose it does have a largest element. X belongs to S omega. A is the largest. So, well, hmm, let me think. Okay. So if X is the largest member of S omega, then what does that mean? Well, let's see. So if any Y is greater than X, what does that mean? That means it can't be its section can't be uncountable, right? It can't be countable. If it's countable, then Y becomes the largest number, right? So that means the only set, no, it's element, I guess, that's greater than X is omega. And essentially, yeah, omega is the immediate successor of X, right? So think about that for a while. If anything is in between omega and X, then that will be the largest member, and that's a contradiction. So omega has to be the immediate successor. Okay. Now, yeah. So since X is yeah, since X is a section such that S of X is countable by definition, right? It's the largest member. So there is a bijection F from Z plus to Sx, right? Now pick your favorite bijection from Z plus to Z minus one, right? Now we're going to define a bijection from okay. So because omega is the immediate successor now, S of omega by definition is equal to X union S omega S X, right? Yeah. Okay. So this is the bijection. Compose it with this what injection or surjection? Surjection. Yeah. Compose it with this surjection. So it's going to be a surjection from Z plus. So we're going to get a surjection from Z plus minus one to Sx. Now define a bijection from Z plus. Actually, no, this would be a yeah surjection, and that's enough. Yeah. Now define a surjection from Z plus to S omega from by defining the h of one to be x, right? So the order type is not the same, and that doesn't matter. The point is we've gotten a surjection from Z plus to S omega, which means S omega is countable, which is a contradiction. So yeah. Okay. Show that that set is countable. Okay. Yeah. So suppose it's countable. This set. Suppose this is countable. Well, by totality, either a set is less than x or greater than x. Hang on. Yeah. Or x is equal to alpha by totality. So what does that mean? That means if we consider the subsets of S omega, which mind you is uncountable, their union is equal to S omega, correct? Now, this is countable by definition of section, any section that's not omega done by omega, and since alpha is not omega, I believe alpha is in S omega, so it cannot be omega by definition. Since alpha is yeah not omega, this is countable. This is countable by assumption towards the contradiction, and this is a singleton, so it's also countable, and their union by theorem is countable, and S omega is countable, so that's a contradiction again. So this has to be uncountable. Yeah. Okay. So for this one, okay, observe that if x naught is countable, then it has an upper bound, right? By theorem. Okay, so yeah, we're going to be using choice a lot now, so let's stop caring about it. Let that upper bound be x, any upper bound, right? Now, if we take the set of all upper bounds, we're going to get a least member, right? So let's call that least member x naught. So this is the least upper bound of that set, and I could have used it directly, but whatever. So with this least upper bound, now what do we do? Yeah, we take this set. Let's see. So S of x naught with yeah, no, yeah, S omega minus S of x naught union x naught, right? This set is going to have a least number, and it's not going to be x naught. So let's call it x1, right? And you can see where I'm going. I just go on forever and say, x n I is equal to S omega minus S of x naught union x naught till x1, and we're taking the least number here, so there's no problem. Otherwise, yeah. So now what? Now, yeah. Now we've defined it for all integers essentially, and this set is a countable set. Why? S x naught is a countable set by definition, right? Since x naught is going to be a member of S omega, and this is a countable set, so their union is countable, and this must also have an upper bound. So let's call it x infinity, right? Now observe that x infinity does not have a predecessor, similar to that argument. So what does that mean? That means this is not the least upper bound, which is a contradiction. Therefore, this set is not bounded, right? The set of all elements that don't have a predecessor. Since it's not bounded by the contrapositive again, well, it's uncountable. So yeah. Okay. Yeah. Question 7 is easy. Let's see. So let what's the set again? Yeah, the sets J naught and J. Okay. So J naught is clearly a subset of J by definition. We just have to show the other quality. Okay. So let alpha. So we have to show that. Yeah. So S of 1 is an inductive set. Sorry, it's an empty set, and the empty set is by definition part of every set. So we're clear. So one is in J naught by pure accident, right? And because of that, let's see. Let alpha be the least element of J such that S of alpha is yeah, alpha be the least element of J such that alpha is not in J naught, right? So S of alpha, since it consists of elements less than alpha, it's going to all of it will be a subset of J naught, and this will imply that alpha is in J naught, which is a contradiction. So by contradiction, what does that mean? That means there is no such least alpha, at least not in J. So yeah, that's the proof of transfinite induction. Okay. I'll just write the general version and then you can figure out the second version, first version on your own. So let's say we have an index set that's well ordered and go into a collection. So this is well ordered and we have and belongs to J, right? Okay. So first we take a subset of J, I'm going to call it Y, to be a set of Y such that A, Y. So we want, what do we want? Yeah, I'm going to call its union as A, right? So AY, yeah, AY intersection, and we're considering the set empty set, non-empty set B of A, right? So we want to find the least member of this set. And yeah, that's all. So Y is the set of all Y such that AY intersection B is not uh, empty. And this set has a least member because B is not empty. So there has to be some Y, right? So we take the least member of this. Let's call it Y naught. And A of Y naught is, and the least member is going to be of, through this well ordered set. Now, A Y naught will be a well ordered set. And since its intersection is non-empty, we can just simply take its intersection, which is a subset of A Y naught. And this set will have a least member. So we take that least member to be A naught, and this will be the least member of throughout the set. Why? Because if it's of a different index, then it's going to be greater for sure by definition of the order, right? Yeah, yeah. And if it's in the same order, then we chose the least number, so we're all good. Okay, yeah. And you can choose it for the index set being 1, comma 2, so it's fine. Okay, anti-dictionary order. Yeah, let's go with the anti-dictionary order problem now. So essentially, there's a whole tail, right? And then it comes up at some point, right? This is like the value of the right, something like that. So the earlier the tail, the later the tail stops, the better. And essentially, yeah, if they stop at the same point, and the higher the tail stops, the better. That's kind of the intuition of the order. I mean, it's written down. Yeah. Okay. So let's prove by induction that there exists a section that has the same order type as Z plus of to the power n, the dictionary order. Yeah. So for n is equal to 1, we simply take the section created by 2. So essentially what? Yeah. 1, comma 2, comma all ones, right? So the section by created by this one would have all ones here after a point and an integer here, right? And here we have the regular order. So there's a direct bijective correspondence between this and Z plus. So that's fine. Now, if you assume the inductive hypothesis to be true, so the section is going to be an essentially 2 at the nth place, n plus 1th place, and all ones before that, however many there are here, and infinitely many ones here, right? So that's going to be the section, and I'm going to show that for the next that n plus 1, this section is the one that we need. So this is already the section from this element is already isomorphic, order preserving the same order type as Z plus to the power n. Now I'm going to show that if you move the 2 here, this is going to be isomorphic to Z plus to the power n plus 1. Yeah, in the dictionary order. Okay, so how do we do that? Well, this part is already Z plus to the power n, and observe that Z plus to the power n cross Z plus is the same order type as z plus to the power n plus 1 in the dictionary order. In fact, I think it's defined that way. Is it? Let's see. Yeah, it is actually defined that way. So, yeah. Hmm. I mean, if you really want to write it down, you can write it using the well-ordered set, which would be here, this one, and that's also another method. But yeah, they're the same order type. So given that, well, yeah, you just map each number here to the first z plus. So it's going to be actually, it's not this actually, it's going to be z plus cross z plus to the power n. So this one would be this one, right? So yeah, you map them in common, and from that you will get z plus to the power n plus 1. And that shows, yeah, for every n we have a section. So we're done. Okay, show that A is well ordered. Well, yeah, so if we take any subset of A, B, well, hmm, yeah, so there's going to be a least, hmm, yeah, you just simply take the least n. So Z plus is a well ordered set, right? You take the least n such that it's not equal to 1. So we have the set of all B, right? We take the set B, and so I'm going to write it as a function n such that f of n is greater than 1, right? Something like that. Belonging to B. Yeah. So you take the least n here, and from that you can get a subset of B, which would be lesser than all the other members. So there won't be anything that's in the outside that's greater. And yeah, you can take a subset of A that's going to be having the same order type as Zn plus 1, this very n, by Zn. Yeah. And the point is this we do know is well ordered. So this has a least number. So we can take the same least number and it will carry. So yeah. Okay, for question 10, I'm solving the general case because we don't actually need C to be well ordered. What we need is a function that gives us a unique value of the member of C for every function that for the function h being restricted to a section of alpha, and we can define that to be h alpha. And I'm essentially quoting section 11 supplementary exercises part 1, and the general case maps onto this specific case because the smallest is a unique element too. So yeah, I'm just solving this case, and this will directly follow. So yeah, first we have to show that their domains are equal. That's actually the easiest part. So let alpha be the least member of C such that h of alpha is not equal to k of alpha. And of course, there's the nuance of their common domains and everything like that. So what does that mean? That means h of alpha is equal to rho of h restricted to s of alpha, and this is equal to rho of k restricted to s of alpha. Now, since alpha is the least member of C such that, yeah, it's a section, right? So it's the least member of C such that, sorry, J, yeah, it's defined on J. Let me just check. Yeah, J into C. So it's from J to C, and yeah, so we do need J to be well ordered. So because alpha is the least, S, for every member of S alpha, H and K are equal. So what does that mean? That means the entire functions are equal, and therefore rho will give the same value. And you can see the contradiction, right? So because of that, for every member of the common domain, they're going to be equal. That's the first part. Yeah, so now we have to show that if yeah, h is a function from S alpha to C, so S alpha is also a well-ordered set because it's a section of a well-ordered set J, then there exists a function h prime from S alpha union alpha to C, right? That's what we have to show. Yeah. Okay, so how do we do this? Yeah, simply define h prime of alpha to be rho of h restricted to S alpha, which will exist because I think we're assuming it's not empty, right? Yeah, otherwise we'll get a surjective function that maps from J to C, because if the restriction is mapping completely to C, that's a problem. And since by assumption there is no surjective function mapping to C, we get to have this set be non-empty essentially. So in the actual example, C minus um, H S alpha won't be empty. In this case, we will get to choose a unique value. So yeah, simply extend the function and we got a new function, and it satisfies the properties because it satisfies it for S alpha by assumption, and for alpha we just defined it. Okay, now we have to check for unions. So K is going to go from, yeah, union alpha belongs to K, S alpha to C. Yeah, okay. So for each alpha in K, we have a H alpha from S alpha to C, right? For each alpha in K. That's no problem. So we need to check the existence of this function. So we just need to check that it's well defined and satisfies the star property at every single member of it. So take any beta that's less than alpha. Well, if beta is less than alpha, it's certainly going to, let's see, actually I'll write beta or not. Yeah. So, okay. Yeah, never mind. This set K certainly has the least upper bound, I believe, right? Yeah. So we take the least upper bound, and I'm going to call that least upper bound beta. And for all alpha less than beta, we have this set. And if we define any function, it's going to be overlaps. That's completely fine. Now, hmm, yeah, so we want to define it for any alpha less than beta essentially, since we have an upper bound. So for that, we'll just take the same row h restricted to as alpha, which we already have. So if we take the union, we have no problem. Is that it? So rho is giving us the unique value, so that's fine. And yeah, hmm. Let me just check. So yeah, I just need to check that every single, okay, yeah. So beta is the, can we even have a least upper bound? K is a subset of J, so J is well ordered, so it has a least upper bound. And yeah, yeah, should be fine. Yeah, okay. Okay, last step, we need to show that by transfinite induction, for every beta belongs to J, there exists a function from S beta to C, right? Such that it's satisfying the row condition. Okay. So if B has a beta has a immediate predecessor, then we take what? So beta is equal to S alpha union alpha by definition then. And there's by definition, by assumption, function from S alpha to C. And we just checked we can do that. We can extend it. And if beta doesn't have an immediate predecessor, then it has to be a union of some set. That's the only way it works. And we can take the union. So if S beta is contained in J, then J beta is contained in J. So by transfinite induction, the entire set J can be mapped in this way. And yeah, since rho is the function that sends a unique element, gives us a unique element from the function, yes, the smallest member of C minus H S alpha is such a function because it never runs out by our assumption. Okay, for question 11, well, either we have a bijection, in which case we're done. So let's assume there is no bijection. Now, between A and B, uh, right, we're going to assume that there's no surjection. If there's a surjection, I can create a bijection right away, or at least an injection right away. How? So first, let us assume that there's a surjective function from B to A to B, and we simply take the least. So A, okay, they're not well ordered, but that doesn't matter. We can use choice. So we just take the least member or any arbitrary choice for the inverse image, and that will be our injective function from. So this is a choice. We're using choice here, but yeah, from choice we can get an injective function from B to A. So we're done. So if we have a surjective function, it's easy. Now, if we don't have any surjective function, then we use the other thing. Yeah. So, well, then what? Then there's going to be an injective function from A to C. Why? Well, it's surjective, and we can take an arbitrary smallest member. In fact, with choice, we can even well order it, but that's beside the point. And yeah, you well order it or you take an arbitrary choice each time. But the point is, you can go along the path, go along the section of each member of it. Yeah, it said using the well ordering theorem, so we're fine. So A and C can both be well ordered. So yeah, you just take the smallest member and each time, and yeah, you're done.